This video lecture will talk about an important theorem in abstract algebra, and this theorem is about a subgroup of a cyclic group is cyclic. So when you have a cyclic group, any subgroup will also have the property of being cyclic. This video will only contain the explanation for this theorem and also the proof. The proof is going to be a little bit long, but it is important, and I'm going to include it because it has very nice ideas in them. All right, so as the title of the theorem says, so let's look at this precise statement. So we have a cyclic group, so that means that this group G here is generated by a single element there. So G is all powers of a single element. So if you have a subgroup of the G, then the subgroup will also be cyclic. All right, so any group of a cyclic group, any subgroup of a cyclic group is cyclic. Now, one of the things I want to mention before we go on with the proof is that the main part of the reasoning of the proof will be finding what is the generator for H. So once we know we have a generator for G because we know it's cyclic, we're gonna extract or try to get the generator for H. All right, so let's go over the proof. So we're gonna assume that G is cyclic and that H is a subgroup of G. That's just the general hypothesis. Now let's write down more precisely what G is cyclic, being cyclic means. So G is cyclic, it means that we have an element in G, so all the powers of that element A will give me the whole group G. So we can express that as saying that G is equal to this set, which remember is all the integer powers of the element A. So as I mentioned earlier, so what we need to do is we need to find a generator of H. Now let me give you a little bit of a picture to tell you more or less what the idea of the proof will be. Now we know for a fact that G, so let's represent G as this rectangle. G, everything inside G is just powers of the element A. Now H, which is a subgroup of G, is also inside, H is also inside G. Because it's inside G, then everything inside H is also powers of the element A. Now the identity has to be inside H because H is a subgroup. So every subgroup contains the identity. So the identity has to be there. And some other powers of the element A. So anything that's gonna be a generator for H will also have to be a power of A. So what the proof is gonna try to do is to try to catch which one is that power of A that's gonna give us the generator. So specifically what we are looking for is what exponent I have to put here for this A, so we have the generator for H. A is the generator for G, the generator for H will be some other power of the same element A. So that's what I mentioned here. The idea of the proof is a generator of H must have the form, it has to be a power of A, and that exponent here, we want it to be in the natural numbers. All right, so we're gonna get rid of a trivial case for H. So when H is the identity, we can actually see that H is gonna be cyclic. So the main part of the proof will be focused on when H is not the identity. So there are two cases. The trivial case when H is the identity, which is something that we can prove quickly. And the other case, there will be this one when H is not the identity. This is where the real work of the proof will go. Okay, so what happens if H is just an element? It's just one element, it is the identity. Well, that is a subgroup of G, of course, and is cyclic. And what is the generator? Well, the generator will just be the identity again, because you start taking powers of the identity, integer powers, and you just get the identity again. So H will be generated by this element, the identity. So trivially, H is cyclic. Of course, that's not the main part of the proof. As I mentioned, the main part of the proof will be this one, when H is not the identity. So when H is not the identity, is not composed with only one element, which is the identity, then in that case is where we have to actually look for what the generator will be. So I will give you an idea on how the proof is gonna go. So we will prove that a generator of H is an element of this form. It has to be a power of A, so it's A to the n0, which of course has to be in H, when n0 is the smallest exponent for which a power of A is in H. So let me explain that with this picture here. So what will be the generator of a generator for H here? So what you do basically is this. The proof is gonna go like this. You look inside H of all the positive powers of A, which some of them are here, and you're gonna select the smallest power of A that is there, positive power of A. That is gonna be the candidate for the generator of H, the smallest power of A, positive power of A that is inside H. So that's basically what the proof will show. Okay, so let's go here. So because we are looking for the smallest, usually when you want to minimize some type of collection of natural numbers, you will have to use the well-ordering principle, which is something we talked about in another proof. The well-ordering principle, it has to do with a set. So what we're gonna do is we're gonna take all the exponents, all the natural numbers, and whose powers of A are in H. So basically what we are doing is look at all the powers of A that are in H. We're gonna make a set made out of the exponent, the positive exponents of the elements of A that are in H. And we will apply the well-ordering principle to this set. Now remember, important thing about applying the well-ordering principle is that we need to prove that the set for which we want to apply the well-ordering principle, that set is non-empty and is included in the natural numbers. So these are two important things that you need to check. Now one of them is easy to check, this one, that A is included in it. Now why is that easy? Because if you look at the definition of what A is made out of elements in N that have this property. So in particular, the elements of A are all elements in N. So it is easy to check that, or to see that A is a subset of N. So that's something we don't have to actually do much about to check. Now we do have to check that that set is not empty. Okay, so let's go about the proof that the set A is not empty. So that's where some of the reason have to be done. All right. So we are under the case that H is not only the identity, or it's not the set of only the identity. If H is not the identity, that means that there is an element in H. Let me call that one. And that element is not the identity, because H is not only the identity. So this must be some element in H that is not the identity. All right. So if that is the case, X is in H, but H is a subset of G. So any element in H is also an element of G. And we know that G is generated by an element A, which we are assuming that G is cyclic. So that means that the element X that is in H is a power of A for some power here, M, and that M is an integer. Now M could be negative, that's possible. The only thing that we can make sure here is that that exponent here is an integer. We cannot assume that is positive because we don't know. Now we gonna say something else about this exponent, and is that we're gonna claim that that exponent cannot be 0. Let's assume that it is and get a contradiction. So what happens if M is equal to 0? So if M is equal to 0, you're gonna go ahead and replace M equal to 0 here. So you're gonna get X equals to A to the 0, like it says right here. But what is A to the 0? By definition, that is just the identity. This is in contradiction with number 2. What is number 2? Number 2 says that the element X is not the identity because we selected one that is not. So that exponent M that is here is not equal to 0. If the exponent M here is not equal to 0, it means that it's either positive or negative. So then we have that m is bigger than 0 or less than 0, positive or negative. So what happens if the exponent is positive? So if the exponent is positive, then we have that a to the m is x. Just read this statement backwards. A to the m is x, and x is in h. So that will mean that this m that is here is an element of the set A. Let's go back here to the set A. What is the set A? The set A contains the natural numbers for which that exponent of A is an h, and that is exactly what this will mean if m is positive. So if m is positive, that means m is a natural number, and a to the m is an h by number 1, so m will be an a. So that will check that m is not empty, assuming that m is bigger than 0. We can get the same conclusion if m is less than 0. So what happens if m is less than 0? If m is less than 0, then we still have that a to the m is an h. Well, but the same thing that we did here. Still the same. X is an h, and x is x to the m. Now, if a to the m is an h, because h is a subgroup, the inverse of a to the m is also in h. So we can conclude that a to the negative m is also in h. Because h is a subgroup, and h is every element in h has its own inverse. Now, because m is less than 0, negative m is in n, and a to the negative m is also in h because of this. These two things here, this one and this one, imply that negative m is an element in A. All of this was to prove that A is not empty. So in any case, A is not empty. So we have a non-empty subset of the natural numbers. Because we have that, we can apply the well-ordering principle. So by the well-ordering principle, this set that we took from earlier has a minimum. So there is the smallest element here. So there is a natural number for which that power of A is the h, and that will be the smallest that is we can find. So let's call that minimum. Let's call it n naught. So that n naught is an element here, so it's a natural number, and a to the n naught is in h. So, and more important than that is that n naught is the smallest natural number with that property. I'm gonna call this whole statement right here, I'm gonna call it number 3 because I'm gonna refer to it a little bit later. So now that will be the exponent that is the candidate for the generator. What do I mean by that? So now we're gonna prove that h is generated by a to the n0, with n0 is the one that came using the well-ordering principle here. So we have to prove that h is equal to this. If we are able to prove this here, that means that h is cyclic, which is exactly what we want to do. Now, proving that these two things are equal, because these are sets. So to prove that this set is equal to this one, we have to prove two inclusions. We have to prove that h is included in this set and the other way around. We have to prove that this set here, the one generated by a to the n naught, is included in h. Now, one of these two inclusions is easier than the other. This one is the easier one, this one. So I'm going to start with that one. So how do we know that this set here is included in h? So that's the first proof, this one. Now, we know by number 3, and number 3, let me go back here, is this one. This is all number 3. In number 3, we have this. A to the n naught is in h. So I'm going to prove that here. We know that. Now, h is closed under the binary operation, and the reason for that is because h is a subgroup. So that means any power, any integer power that I take of a to the n naught, that integer power will also be in h, because h is closed. So that means this set, which is made out of the all integer powers of a naught, all these elements here will be elements of H. So that means this collection is in H. So that proves this inclusion. So that's the easy part. So this one here is done. The harder inclusion will be this one, to prove that H is included in this set here. So let's do that proof now. So let's prove that H is included in this set. Now, how do you prove inclusion? The standard way to prove inclusion is that you take an element here, and then you have to prove that that element is here. So let's call that element X, for example. So let's take an X in H. The goal here would be to prove that X is here. So we will end up proving that X is a power of A to the n naught. So let's assume that X is in H. So I'm going to call that number 4. Now we know that H is a subset. It's a subgroup, but it's in particular a subset of G, which is all powers of A. So that means that X itself has to be also a power of A. So power A to the T, and I'm gonna call this number 5, where that T is some integer. Now remember, what we need to prove is that this element X is a power of A to the n naught. So that would be the idea for the rest of the proof now. Now, how do we do that? So we're gonna use the division algorithm between the number T here, this integer T, and n naught, which is a natural number. So we're gonna use T as the dividend and n as a divisor. So we're gonna take T divided by n0 using the division algorithm. So if we do that, then the division algorithm tells me that I get two unique integers. One of them is the quotient Q, and the other one is gonna be the remainder. And what we get is this. So the division algorithm tells me the dividend is equal to the quotient times the divisor plus the remainder, and the remainder has to have this property here. It has to have this hold this inequality. Remember, this is also important. So the remainder has to be bigger than or equal to 0, and it has to be strictly less than the divisor here, which is n0. So it has to be less than the absolute value of the divisor, but here n0 is positive because n0 is a natural number. So we're gonna call this one 6. Now, by number 5, which is the one that I have here, X is equal to a power of A. So if that is the case, I can replace this T here. So X is equal to A to the T. I can replace this T by this equation that I have here. So I'm going to replace T by Q times n naught plus R. So I'm going to replace the exponent here. We have done this trick in some other proofs as well. So I'm going to split this up using the laws of exponents for groups. So this is addition. This is going to split into star A to the Q times n naught star A to the R. Now, you can also apply the law of exponents here. So A to the Q times n naught is the same as A to the n naught to the Q star A to the R. So what all of this sequence of equalities here mean is that X, this element, is equal to this expression that is here. And that's what I have over here. X is equal to A to the n naught Q star A to the R. Now I'm gonna do the following thing. I'm gonna apply the operation, the binary operation on the left, but A to the n naught to the minus Q. So that means I'm gonna start here on the left, on this side here, on this side, on the left, and I'm gonna get this expression. So actually this should be reversed. So let me correct that in here. So when we have that, so when we start on the left, so I'm gonna start on the left here on this side. So then we will get the following thing. We will get A to the n naught to the minus Q star X. So this is here on this side. And if you do a star here on the left, this element and this one are the inverse of each other, so they kind of just, you can say that they cancel out here when you start here on the left. So you're gonna get this expression here. Now what happens in this case? If you look at the left hand side, so let me make that here. This is an element in H. This is an element in H. So what is that, an element in H? Because we started from there. X is in H. Let me scroll all the way up. So it's right here. That's number 4. X is in H. So let's just say Y. So this is by 4. So this is by 4. Now, how about this element that is here? This is also an element in H. So let me write that down. Element in H. And why is that? Why is that an element in H? Well, let's look at this. A to the n0 to the n0. This is an element in H. Why? Let me scroll all the way back here. So it's here, but the main reason is because we apply the well-ordering principle. A to the n0 is an H. That's by number 3. Let me scroll all the way back down. So there's an element in H. So this element here, A to the n0, is an H because H is closed, and an integer power of that is also in H. So this whole thing here is in H. So what we have is, this is an element in H. This is also an element in H. What that means is A to the R is also an element in H because H is closed under the binary operation here. So this proves that A to the R is in H. But there is a property of R that we haven't used yet. R is bigger than or equal to 0 and less than n0. Now remember that n0 has the property that is the smallest positive exponent that is in H. So A to the n0 is the smallest positive exponent that is in H. But what happens with this reasoning that we just did here? A to the R is in H. That means R cannot be bigger than 0. Because if it is, then I will have found a smaller exponent than n0 that is in H. And that is a contradiction because I know n0 is the small, n0 is the smallest. So the only possible way, which is this and this could happen, is if R is equal to 0. So then that means that that exponent is 0. Now, if we replace R0 into number 3, or into the division algorithm, remember that T was equal to Q times n0 plus R, but R is 0, so we will have this. So T is equal to Q times n0. Now, this will allow us to prove that X is a power of n0. Why? Because remember, X was equal to A to the T. If you go back into the argument, you will see that X is equals to A to the T. But what is T here? T is this one. You can replace it by Q times n0. And this can be rewritten as A to the n0 to the Q. What does this mean? It means that the element X is a integer power of X to the n0. That is, X is here. Now remember, this whole argument, how we went was like this. We started with an element X in H, and we ended up proving that X is in here. So that proves this inclusion. So what that means is, now these two sets are the same, because remember, we proved the other way around too. H is included in this set, and we also prove at the beginning of the proof that this one is included in H. So that will prove that these two sets are the same. If these two sets are the same, that means that H is cyclic and is generated by this element here, A to the n0. So that proves that H is cyclic. So that is the proof of the theorem. Now, I know this proof was a little bit longer, and it involved a couple of things that we used before, the well-ordering principle and the division algorithm. One of the important parts, and let me scroll all the way up to the picture I had at the beginning of the proof, is how you get the generator for H. That's the main part of the proof. That's the main idea. The main idea is how you get the generator. So here, let's go over the idea again. So G is cyclic, so everything inside G is all powers of A. How do you get a generator for a subgroup? Is a power of A where this exponent is the smallest exponent, positive exponent that is in H. That will give you the generator for H. That's the main idea of the proof. G is cyclic, powers of A, all powers of A are all G, and any subgroup of H of G will also be cyclic, with the generator being A to the n exponent, where this exponent is the smallest positive exponent that is in H. Now that is one of the generators. H could have more, but that's one of the ones that works here for the proof. All right, so that's all I have to say about this topic. This is an important proof and result because of the idea that it has in them. All right, so that's all I have to say for this video. Take care. Good luck.